Hey everyone, Mr. Newman here, and on this video we're going to learn about the derivative. What are derivatives and what are they used for? But to start, I need to build your intuition up for that for a bit. So we need to look at this graph, this function, and I need to ask you, what is the slope of this graph? Take a moment to think about what the slope of this graph would even mean. Alright, so first thing you might notice is that for this graph on the right here, we can't find the slope like we normally do because it is curved. Hopefully that was your first thought. And maybe some of you also thought about, well, we could approximate the slope with a line. And there are lots of different options here. For example, if we wanted to find the slope at x equals 1, that point is 1, 1, we could draw a line on either side of it and say, hey, that's an approximation of the slope. That would give us 2 points and we could calculate the slope. We could also draw a line right through the point and hope that that line is tangent to the curve, and that would give us a good approximation of the slope as well. Let's give a few definitions here. First of all, that first line I mentioned is called a secant line. That is a line that intersects the curve at 2 points. It could actually intersect it at more than 2 points, but we use 2 points to calculate the slope, and that is what a secant line is. Those 2 points there. Let me show you how we would calculate the slope. You've probably heard of rise over run or delta y over delta x. I use that instead of the formula because you can look at this or easily subtract and calculate, oh, that is a rise of 3 and a run of 3. So the slope of that secant line is 3 over 3, which is 1. We're going to use that on the other side of the sheet here. Meanwhile, the tangent line is a line that, like this, that intersects the curve at exactly 1 point locally. Okay? Now the reason I have to include locally is because if the curve, kind of like a sine curve or a cosine curve, went up and down, there are tangent lines that intersect at more than 1 point, but if you zoom in, the tangent line goes along with the curve, but only touches the curve at exactly 1 point. So, what is the slope of this line? Well, you could look at it and guess. You could say, well, it looks like it's going kind of over 1, up 2, maybe up 1.5. But the problem with that is that totally depends on how I draw it. This could be an equally valid tangent line to my eyes, or the green line there, or the blue line. So who's to say that I actually drew the correct tangent line? We need to do some math to figure this out. And that is the problem that we are dealing with here. It's called the tangent line problem. Our goal is to find the slope of the tangent line, but the problem is, whenever you calculate slope, you need 2 points to calculate slope. But a tangent line only gives you 1 point. You only know that 1 point where the line touches the curve. So, next thing I would like for you to do is I want you to type in or click on the link, go to this Desmos link. And what I want you to do is I want you to play around with it. What I've got here is a secant line, meaning it intersects at 2 points. And the black dot is our point that we're trying to find the tangent line through. What we're going to do is we're going to have this secant line. So you want to keep that black dot in one place. What you're going to do is on Desmos, you're going to grab the purple dot and you're going to drag it towards the black dot like this. And I want you to see what happens to the slope when the purple dot is right on top of the black dot. Go ahead and try that now. All right. Now that you've tried that, now that you're back and the purple dot was right on top of the black dot, it should have said that the slope is undefined. The reason for that is because we only have 1 point. And if you're trying to calculate slope with rise over run, your run is 0, so you're dividing by 0, and that is a problem. Well, so here's my next question. I want you to see, as the purple dot approaches the black dot, what is the value of the slope approach? And you can approximate this by typing in values for h. You'll notice h is a slider. I think it's right below the slope on the left there. And you can drag that to the left, but to get really, really close values that are close to 0, because h is the horizontal distance between the dots, you should type in 0.01, 0.001, and 0.0001 to see how close you can get to 0 without actually typing in 0. So yeah, h, like I said, is the horizontal distance between the two secant points, between the purple dot and the black dot. And one last thing you should notice before you do this, well, I'll let you do this first and we'll observe something. All right, did you get the value of 2? You should have gotten some values for the slope that are really, really close to 2. And you should notice something, or you should, these 0.01, 0.001, 0.0001 should remind you of something we've been doing recently, and that is limits, and that's going to come into play in just a moment. All right, let's flip on over the back and see what is going on with the algebra of this situation. Oh, before we do that, I wanted to write down the actual equation for the tangent line at x equals 1. Notice it's y equals 2x minus 1, so our approximation of it, of the slope being 2, is actually correct. The slope is exactly 2 for the tangent line. And so we need to look at the algebra and figure out how do we get that. All right, so the question is, what is the slope of the secant line? Here's how I calculated that slope. Slope is delta y over delta x. That's rise over run. And let's just label a few things on this graph here. Notice that the x value of the black point is x, and the x value of the purple point is x plus h. So the question is, all right, well, what's the horizontal distance between them? Well, I did say that earlier, but you can also subtract x plus h minus x, leaves us with just h. So this distance right here, the horizontal distance there, is exactly h between those 2 points. I'm going to leave the x plus h here so we can think about this in a moment. The y values, the y value of x is f of x, that's for any function, and the y value of the purple point is f of x plus h. That's because the input is x plus h at that point, the x value is, and we plug that in and we get f of x plus h. So what is, if the run is h, what's the rise? Well, you subtract those two values to find the difference, to find the length of that rise. So it's f of x plus h minus f of x. That's the vertical distance there between the purple point and the black point. So we have our rise and we have our run. Let's put these into our formula for slope. The rise is f of x plus h minus f of x, and the run is just h. So you notice that's where we got this from. The slope of the secant line is rise over run. That's f of x plus h minus f of x all over h. A few things that you should notice is as you drag this point, that purple point on your Desmos graph, as you drag that down and to the left, h gets smaller and smaller, to the point that if h was actually 0, that'd be a problem because we're dividing by 0, and you can't divide by 0 in a fraction. So that is why the slope is undefined. But what is the slope of the tangent line? What if instead of saying let's make h equal to 0, what if we calculated the limit as h got closer to 0? That would be like saying, well, what if we could make h 0 and still calculate the tangent line? That's exactly what the limit does. As h approaches 0 of the slope will give us the slope of the tangent line. So m equals, the slope of the tangent line, m equals that little expression right there. And that, you guys, is the derivative. Real quick, before we go too much further, I want you to notice that it's kind of like saying this is the limit as our secant line approaches the tangent line. As our secant line gets closer and closer to being a tangent line where it only touches in one point. It's touching in 2 points all the way up until you move it right on top of the purple dot, right on top of the black dot. And when those are on top of each other, that's when we have a tangent line. So, but we can't calculate that, we need the limit. So this is the derivative. And we write the derivative with that little f apostrophe. You see this right here? I don't know if that's clear enough. I'll write it right here. It's f, we call that f prime, okay? F prime. And that means the derivative of the function f. And it's equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And you should definitely memorize this formula. You're going to be using it a lot in the future if you continue with math, and this is going to be, it needs to be memorized in this class as well. So let's practice trying to use it once. Well, find the derivative of f of x equals 3x squared minus 2x. What I'm going to do is I'm going to first write down the limit as h approaches 0, starting with my definition of the derivative. I'm going to real quick on the side write down what is f of x plus h. Well, that's plugging in x plus h everywhere that I have x into the function. So that is what you get when you plug in x plus h into our function. I'm going to put that in brackets. That's just a fancy parentheses to separate it out. So there's f of x plus h minus f of x. The f of x is in black, so 3x squared minus 2x is my function, f of x. All that divided by h. At this point, you guys, this is a problem that we have done before. So I'm going to be referencing things we've done over the past several units, and the only new idea is what does this thing mean? But you guys have actually already found out limits like this before. So let's simplify the numerator. We're going to square out the green and multiply all those numbers out. And we'll also distribute the negative, that blue negative there, which is why we get the plus 2x at the very end. And you notice some things add up to 0 or subtract out. They subtract out as well. And we're left with this right here. Notice we still can't plug in 0, so I'm going to factor out the h. Also notice I'm writing down limit as h approaches 0 every time because that's very important to include. And we divide out the h. We get the limit as h approaches 0 of 6x plus h minus 2. Plug in 0 here, and you get 6x minus 2. And that, ladies and gentlemen, is our derivative, 6x minus 2. So the derivative of f of x equals 3x squared minus 2x is 6x minus 2. Great. What does that mean? Well, here's what the derivative means to remind you of what we talked about in the front. The derivative, or in this situation, the derivative is the slope of the tangent line at x is 6x minus 2. That's what the derivative means for this function. It means that the derivative is the slope of the tangent line. Let me give you a specific example. So notice I graphed our function f of x over here. So the slope of the tangent line at 0, when x is 0, is, well, plug in 0 into f prime. 6 times 0 minus 2 is negative 2. That means our point right there, 0, the slope of the tangent line at that point, the tangent line at x equals 0, that has a slope of negative 2. We found the slope of the tangent line. Let's figure out the tangent line, the slope of the tangent line at x equals 1. Well, plug in 1 there and you get 4. So if my tangent line point is 1, 1, that's the tangent line at x equals 1, and it has a slope of 4. So, before I get too much further, the derivative, this formula I found here, right there, the 6x minus 2, that's a generic formula that if I want the slope of the tangent line at any point on the graph, I can just plug in that point, the x value of that point, and the derivative will tell me the slope at that point. So you go, cool, we did all that work just to find the slope of a tangent line. What's the big deal though? So I'm going to take a moment in this video and back up and kind of take a bird's eye view, because a lot of times we do all this math and we get lost in the details and we wonder why are we doing all of it. I want to tell you some applications of the derivative. We're not going to be able to do it in this video, but do them specifically, but I want to tell you how they can apply, and you will get to a lot of these in calculus. So some of the applications of the derivative include the most common one is the instantaneous rate of change. That means how fast is something going, or how fast is something changing at a moment, at a specific moment. You can always find the average rate of change by calculating the slope, but the instantaneous rate of change requires the derivative. It requires calculus to find out. So examples of this are how fast is ice melting? That'd be in climate change. Or how fast are trees growing? You can find that out in biology. Or how fast are cars driving? That might matter in criminology. For example, radar guns actually use the derivative in their calculations to figure out how fast a car is going. You can also use the derivative in optimization problems. So an example of this would be, how expensive should you set a price of an item to maximize your profits? If you make the item too expensive, nobody's going to buy it, or very few people will buy it, and you won't make a lot of money that way. If you make the item too cheap, if you set the price too low rather, then what will happen is people will buy it, but you won't make very much money off of each item. So how can you maximize your profits is a calculus problem, is one where the derivative will give you the answer. How much medicine should you administer to keep a patient healthy? This is a good one, because if you administer too little medicine, then it does no good for the patient. But if you administer too much medicine, then that actually can be dangerous for the patient in other ways, especially with side effects. So you might think, oh, nurses and doctors, they just kind of guess or whatever, or people that, the drug companies, they just say, well, about this much. No, there's actually a whole lot of research that goes into how much Tylenol you should take if you're sick, or how much Advil you should take if you're sick, because that is a very important problem, and they use calculus to determine the maximization of those, or the optimization of that. Another thing you might be interested in is computers. How fast should the processor run so it doesn't melt in the long run? You can actually change a processor to make it run faster and faster and faster, but the problem is, currently the problem with our computers is that they overheat. And so if you run a processor too fast, it gets too hot, and it can break down the processor. You might think, oh, well, that's a simple problem. Just figure out how much, how high can you run it so it doesn't overheat. Well, the overheating problem is an optimization problem, because if you can run it at slightly too hot, but then, the problem is it will break down in less time than if you run it way, way, way too cold, then your computer's going really slow. So all these are just a taste of what this derivative problem, what this slope of the tangent line, how this is so important. And this opened up a whole new field of calculus and revolutionized the way we understood physics, understood the world around us. So thank you for watching, and I hope you learned something.